Thank you so much for being here for this paper session number 9, both speakers and attendees. I am Ines Elisabeth Cain from R2M Solution, and it is my pleasure to be chairing this session. So here is the agenda for today. We will start with a presentation from Igor Perevozchikov from R2M Solution. He will be presenting the project premises, impact of predictive maintenance and IoT on the SRI. Then we will continue with a presentation from José, Humberto, Matias, de Paula, Filho from ArcelorMittal. So the subject is life cycle assessment of an office building, influence of the structural design on the embodied carbon emissions. The third presentation for today will be from Nicolas Rehault from Fraunhofer Institut for Solar Energy Systems on increasing transferability for automated fault detection and diagnosis in HVAC systems through a hybrid AI methodology. And this last presentation for today will be from Nirvana Marting from LIST on social LCA of recycled PVC products. So let's start with the first presentation from Igor Perevozchikov. You can click here with the mouse.
Okay. Thank you. So, good afternoon all. I'm happy to open this last on-site paper session to finish the Sustainable Places Conference. My presentation will be focused on the premises project and the impact of the predictive maintenance and IoT on the SRI, Smart Readiness Indicator. So the premises project has been financed by the Sustain Open Call program. So it's the program financing different kinds of innovation action initiatives in order to provide them additional impact in order to go to the solutions who has a TRL, advanced TRL, so TRL 6 and TRL 7. This is a project with only 2 partners, so it's coordinated by Osmos Enterprise. It's an industrial partner who is developing HVAC system, and R2M Solution, which is the second partner. So, to introduce the predictive maintenance, why we are speaking about it. So I think you are already heard this kind of questions from and phrases from building owners, from energy managers, and asset managers, that we pay higher cost for maintenance. The cost for maintenance of buildings is higher from one year to another. The cooling units, the ambient lighting is not more working, is not more switching on automatically. So the window motors are broken, etc. So in order to give some answers on these questions, the predictive maintenance term is introduced. So the predictive maintenance terms uses data analysis to identify different kinds of deviations and operational anomalies and potential equipment defects in order to enable timely repair before failures or different kinds of of different kinds occur. So it's based often on sensor and meter data. We need the field data first from the technical building systems in order to analyze it and to provide recommendations to do repairing of systems in just in time. So if you can see on this diagram between three types of maintenance of building assets, the predictive maintenance is situated on the high of this pyramid. So it presents the most optimized way for building maintenance and the most proactive. So the challenges of predictive maintenance are numerous. The first of challenges, it's high initial costs. So this kind of system of enabling predictive maintenance is composed often by software part and by hardware, and so presents at the beginning higher cost to be implemented. After that, we need to collect and to manage monitoring data from not only the energy data, but the data about the status of different technical building systems. We need to ensure the integration with legacy systems. We need to sometimes to install gateways in order to be collected directly to heat pumps, to cooling systems, etc. So we need to be sure also about the accuracy and quality of data, and the sensor reliability and maintenance. And so we don't forget also the cybersecurity risks associated to any kind of software solution. So the predictive maintenance is often could be also used for energy optimization of technical building systems, because most deviations involve overconsumption. So if we use the predictive maintenance for this purpose, we analyze the energy consumption data in a precise way, we can identify deviations associated to systems, we can prevent the failure. So anticipation these deviations can automatically increase the energy performance of installations of smart building. And the last one, it's the need to contextualize the data in order to find a way to interpret this data. So we need, at each moment, we need to know what is the meaning of the data we are collecting in order to interpret them in the best way. So the objective of Premises project, if you can see that it's a relatively short project, only 9 months of duration. So this will it will end this year. So the objective of this project is to introduce an approach of predictive maintenance of HVAC system associated to the IoT devices and artificial intelligence algorithms to a smarter building in order to prevent the failure of systems and in order to ensure the energy optimization of building use. Actually, the premises, before the beginning of the project, the TRL technology readiness level of premises solutions has been situated at the level TRL 5. So this project allows to go to enhance the TRL level of this solution, going to real life testing on a real building, and also in this way going to TRL 7. So the innovations introduced by this project, it's firstly low installation costs. In difference from other solutions of this type, the premises solution is not associated to costly devices, costly systems. It's associated to some kind, not really a low cost, but it's associated to IoT sensors that don't need of any wires to be installed on site. In this way, can be adapted for rehabilitation projects. The return on investment after the installation of a such system is situated under 1.5 years, which is also relatively short. The premises solution enhances the SRI score of building, and we will see after the impact of this solution on the enhancement of the SRI score. And it's ensure the solution propose an efficient integration with existing systems by normalized protocols like Modbus protocols, like BACnet and other standardized protocols. So the architecture of premises solution, you can see it on this picture. In buildings equipped with BMS systems, controllers, sensors, and actuators, there is a box, so a kind of hardware which is installed into existing building, which is connected to the supervision servers or BMS systems by standardized protocols, and which send the data to a cloud solution. So, which is finally the heart of premises solution to be analyzed. So this data, once analyzed, ensure the feedback to BMS users by email or by other ways. We plan, so we have implemented 2 algorithms in the framework of this project. The first algorithms, it's control loop algorithms, which allows, by analyzing energy consumption data of HVAC systems, allows to identify a drift, so a deviations of energy consumption, and send the alerts to final users in order to say them, please pay attention because there is an abnormal consumption at this moment for HVAC unit number 10. So in this way, if the final user, the energy manager, pay an attention, he can identify a potential broker of the system, can proceed to avoiding risk of failure of a broken system, can proceed finally to a maintenance in order to avoid it. And this can allow us to back to normal situation after this detection of deviation. And the second algorithm is the meter system algorithm, which is based on the using of virtual meters, we call it. Virtual meters, I mean here that the system which is analyzed, which are analyzed in the framework of the premises solution, are modelized virtually. There is a virtual model which is constructed, and at each moment of time, the real data from this HVAC systems compared with a virtual model, which is adjusted, of course, according to different kinds of weather data, according to other constraints. And if there is a deviation which is detected, once more time, an alert is sent to final user in order to verify where is the problem. Just to add here that the premises solutions is not judge the reason of this difference between virtual data and real data. Here, the premises solution only alerts that there is something abnormal situation, and in this way allow to avoid some failures and some brokens of the equipment. In project we have 3 KPIs which are established. So the reliability of algorithms implemented will be going up to 85%. The return on investment less than 1 year or 1 year and a half, and SRI score improvement more than 50%. This solution will be tested on the pilot site of the project, which is in the building of Osmos. It's the headquarters of Osmos company in southeast of France, which is a mixed-use building, mixing offices, manufacturing, and warehouse usage. A relatively small building dealing with 1,100 square meters, and this is a recent building constructed in 2019 with 3 levels and about 35 users inside. So this is the project work plan, how we process it to achieve the goals and the KPI of the project. Firstly, we have selected the IoT devices to be installed into the building. Thank you. Together with the software parts associated to ORIS BMS and Home Assistance to be installed. Secondly, we have implemented the artificial intelligence driven algorithms, which has been presented just before. We proceeded to testing of these algorithms, and the last 2 parts has been focused on the SRI analysis of initial state of the buildings without any devices and systems implemented, and simulation of SRI score of this building with the premises solution implemented. And the last part, it's the assessment of the KPI of the project. So this is the initial, the baseline SRI score of the buildings, which is associated to 22.28% and to the SRI class C. So just a small remark here that in France, we have adapted a different names of SRI classes in difference from another member states of European Union, and so that's why you can see that the score of 22% of the SRI score is associated to the class C. So in general methodology, precise 7 classes of the SRI from G to A, and in France we have adapted the names of the SRI classes from D to A++, so 3 plus. And so the score of technical domains and impact criteria, you can see it just below on this slide. The improvements after the analysis of firstly of the building, of needs of the project, we have proposed SRI score improvements, how we can we can enhance the SRI score of the building. And so the first thing to be proposed, it was to implement a premises solution. So it's the main goal of the project. But this solution should be associated to the sensors and the meters to be installed into the building. So there are some sensors and meters already installed, associated to some kinds of monitoring software for temperature sensors, for HVAC units, for domestic hot water. But we have chosen to complement this installation by additional IoT sensor for temperature, relative humidity, and indoor air quality sensors, and to also to go to a more sophisticated building management systems of classes B or A. And the third recommendation was to provide flexibility capabilities by connection BMS supervision server to electrical grid signals. This is finally the architecture of the solution which has been implemented on site with temperature, humidity sensors, smart plugs. You can see the server, the central server smart box, which includes Home Assistance or SBMS with Data Broker Mosquito, and a premises solution which is hosted into the cloud, which interacts with ORS-BMS by emails, and the HVAC unit connected to this solution by Modbus TCP protocol. And finally, after the implementation of the premises solution, so we have simulated the score, the final score associated to the implementation of predictive maintenance, which is about 36% of the SRI score, which is associated to the class B. If you can see, we have one of the KPI which is related to the SRI score improvement, which is associated to 15%. We are at least almost achieving this KPI. The domains which are the most impacted by the installation of the premises solution are the maintenance, sorry, not the domain, but impact criteria. So it's the maintenance impact criteria, information to occupants, and convenience. With also some small modifications associated to energy efficiency, comfort, and health. And regarding the technical domains impacted, so you can see that monitoring and control domains, which is mainly impacted by the installation of premises predictive maintenance solution, followed by ventilation technical domains. And to conclude, the impact of premises predictive maintenance associated with IoT devices in a non-residential building impacts mainly the SRI services detecting faults of technical building systems and reporting of performances associated to heating, cooling, ventilation, and monitoring control. So we are at about 14.5%. And regarding the criteria, as I said, the maintenance criteria is raised by 42%. It's the biggest score. The small addings here that if we implement a kind of flexibility control solution, allowing the management of building based on grid signals, this kind of measures has the biggest impact, which on the SRI score, which is achieving almost 12% of enhancement. So thank you for your attention. If you have some questions, you can ask Ines. She will pass me your questions. Thank you.
Thank you, Igor Perevozchikov, for this presentation of the premises project. We will try to have a Q&A session at the end of the paper session if time allows it. And we will continue with the second presentation from José, Humberto, Matias, de Paula, Filho from ArcelorMittal on life cycle assessment of an office building. Thank you, Igor. Bye.
Thank you. My name is José Humberto, so I'm about to present a little bit about life cycle assessment and how structures they influence on the embodied carbon of especially office buildings. First question, do we have any architects or engineers here, civil engineers? So, yeah, have you ever done any design optimization based on that the main objective was to reduce the embodied carbon and not cost, let's say? No. I guess this will come in the near future. I hope so, at least. Yeah, if I may start, we can jump directly into this slide. Yeah, so I guess that this is no news to all of you. So we know that 37% of CO2 emissions can be attributed to buildings and the construction sector. We have seen a lot, and even in presentations during this conference, that a lot of efforts have been put to reduce the operational carbon of office buildings and buildings in general, putting a lot of stress, a lot of awareness in the embodied carbon, because these were architects and engineers that we can really influence in the embodied carbon by proposing, let's say, the right materials, such as high-strength steel, for example, and also coming up with clever and smart engineering solutions, as we'll see. So if I may speak a little bit about life cycle assessment, is a scientific and quantitative method to assess environmentally relevant process. So in our case, it will be the construction of an office building. Important to say also that LCA, we have an ISO standard that regulates all the methodology behind. So it's the ISO 14044 that defines some steps that an assessor needs to follow in order to conduct a life cycle assessment. So we have first the goal and scope. So here we are actually defining what and why we are assessing. We have the life cycle inventory that we collect all the data to perform the assessment. The life cycle impact assessment. So here's where we are actually measuring environmental impact indicators. So, for example, global warming potential. And after, the idea is that we're going to interpret all these results and see where we can, let's say, optimize and focus on relevant processes. So for our specific assessment, what we want to do is to assess the embodied carbon of equivalent structural options, but that they are composed by different materials of an office building, which is located in Luxembourg for a service life of 50 years. So here we have in this bottom table the function unit that all these equivalent and different structural options needs to answer, because that's how we can in the end compare them. So our office building looks like this picture on the top right. It's an L-shaped office building that has a gross floor area of 15,552 meters square. All the results that we're going to see later on, they're based on, it will be in function of meter square, and we can perhaps have a look in some of the most representative dimensions of the building in the bottom right table. We have a depth of 13 meters of the building. The length of one leg of the L is 78 meters. We have two underground levels, so those are the levels below the orange line. The free height of the typical floor is 2.7 meters, and the ground floor, the free height is 3.5 meters. This is just the architectural layout of the typical floor. I don't know if it's very readable, but yeah, just to say that We have a symmetric building. Perhaps I can launch the laser point to be easier. So yes, the building is symmetric in this axis. So we have the same architectural distribution of spaces between the two sides of the building. Then, speaking a little bit about our object of assessment, so the structural options that we are going to be assessing, we have a composite steel concrete option, a prefabricated reinforced concrete option, and a timber option. Those, I would say, here in Europe, they are very representative from the construction market, so that's why we chose those. We engaged an independent design office to conduct the design, to have really an independent opinion on how those quantities and weights would be later on. Important again that, of course, that we are, all these structural systems, they were designed following the same boundary conditions, such as design assumptions, the location of the building, as I said, soil conditions, safety requirements, and all the actions on the structure. Jumping already in the first variant, so it's the steel composite variant, so option 1. Here we see the structural grid. So the grid is like how we divide into modules throughout this length of the building. So we have the columns that are placed every 8.1 meters, and we have a free span of 13 meters. So basically, so we don't have intermediate columns in this direction of the building. And we have cellular beams that we call the Angelina beams. So they have these sinusoidal openings that are quite useful because we can have all the systems of your building going through. We can really save in height here. So we have a composite floor in which we have a steel deck that uses is being used also as a formwork for the ready-mix concrete that is cast in situ on top of the beams. We have also secondary beams that are placed every 2.7 meters, and that's the direction of the span of this flooring system. The second option is a prefabricated reinforced concrete option that has the columns placed like the solution before, every 8.1 meters. But in this case, we have the outcome of the design is that they saw that it was needed to place an intermediate column. So we don't have a free span anymore in this direction. We have a 5+8 span configuration, and the floors are spanning in the 8.1 meter beam to beam. And the final option is the timber option, where the columns are spaced slightly closer, 5.4 meters. We also have the same intermediate column configuration, 5+8, in this direction of the building. With that being said, speaking about the boundaries of the assessment, so we follow the framework which is defined in the EN 15978 that defines the life cycle of the buildings into modules. So we considered in our assessment the product stage, the construction process, the end of life, and benefits outside the system boundaries, so the module D. So everything that we choose to do in the end of life, we may have burdens or benefits, and those are accounted in this module D. If you have a look further, this diagram here is really to list all the sub-processes that were considered in each of the life cycle stages. Maybe it's worth to mentioning here that we included in the assessment some specific building parts that we would like to have a look. It was the foundations, the underground retaining walls, the cores, the frame and floors, and the roof, so only structural elements. So here we are not assessing, for example, the envelopes or HVAC systems, finishes, and so on. Some very technical LCA terms here that maybe I'll concentrate in just in this one. I guess it's the most important for us here, is that often we are asked if usually when we present results like this, we say, okay, but is that true for any building, anywhere built in the world? So we would wish to answer yes, but unfortunately, those results, they're very conditioned to the boundary conditions in which the life cycle assessment was made upon, and also the physical location of the building. But I would say that those results could be quite representative to the European region, I would say. Going further, speaking about now which environmental indicator and LCA assessment methodology, impact assessment methodology we chose here. We are just assessing global warming potential, and it's quite easy to explain. Today is what we hear in the media almost all the time, and we can say that it's one of the most pressing environmental issues of our time. Now about the method that we use, so you're going to see later that our assessment is very much based on the use of environmental product declarations. And we'll see also that we chose so environmental product declarations, EPDs, that are in line to two versions of the EN 15804. And because of that, we could have some incompatibilities in the assessment that I can briefly explain. So the previous version of the standard would declare global warming with a single indicator, and the new version now declares in 3 sub-indicators. So GWP fossil, biogenic, and land use and transformation. So which one to choose when making comparisons that are mixing both of these standards? So we can ensure, let's say, a partial compatibility, meaning that if the EPD that we are using is based on the old version of the standard, we have only one indicator to choose, so we choose that, but we remove from the carbon accounting the biogenic storage. So I don't know if you ever saw an EPD from wood. Normally, when the wood is growing, you can absorb CO2 emissions, resulting in a potential negative global warming potential. So that was removed from the assessment, because that is what is done in the new version of the standard. So basically, if we use an EPD that is in line with the new version of the standard, we are using just the sub-indicator GWP fossil. So that's how we guaranteed this partial compatibility in our assessment. Here, just to highlight some of the assumptions that we need to make in order to assess all those life cycle stages that I mentioned before. For the transport, we have materials, we choose a transportation type and distances. For construction site, we only include in the assessment the waste that is generated in the construction site. So basically, we add some percentages that are going to be the surplus of production that we are going to account as waste. And here, very important end-of-life assumption. So what's going to happen with the building when it's deconstructed? So we are saying that all the steel hot rolled sections that we have in the building is going to be majorly recycled and reused. Flat steel will be recycled. Steel rebars, they're going to be recovered, recycled, and some parts will be lost and potentially landfilled. And reinforced concrete, I like to use the word downcycling, because actually when you cannot recycle the concrete, because if you see in the hierarchy of use, if you recycle, it has to have the same, let's say, hierarchy. So if you recycle structural concrete, it needs to be structural concrete again, which is not really happening today, unfortunately. So the downcycling, basically, we are going to crush the concrete and use as replacement aggregates, for instance, in backfilling material for road construction. Here we have the life cycle inventory. So that's the main outcome from the structural design, is the bill of materials that in this chart is represented by the building weight. So we see the influence of the different building parts in the weight of the building. And we see that if we compare the steel building with the prefab concrete one, we can reduce the weight of the building 36%, and that we'll see later that will have major implications in the global warming potential. Here is just for the sake of transparency, we listed all the materials that are present in all of the variants and all the data sets, in our case EPDs, that were used to estimate the global warming for each of these materials based on their quantities. I would like to highlight these three materials here. So the structural steel sections, steel coils, and steel rebars. And you see that there is this word hidden here, X-carb. So that's the low carbon emission steel that ArcelorMittal is producing. Later also I will show like how we can achieve this lower embodied carbon in for these products. So how we calculate global warming potential finally, so we have in one side all the quantities from materials, and for each of the materials we have the associated EPD that is telling us emission factors for global warming for each of those life cycle stages. So basically in the end we multiply those and then we can end up having this assessment. Here, just to also, for the sake of transparency, illustrating all of the emission factors that are present in the EPDs that I mentioned before. So what is this low carbon emission steel from ArcelorMittal? So basically it relies on the production of steel using an electric arc furnace, meaning that we have up to 100% recycled steel content in the production of steel products, and with the addition of 100% renewable electricity. So by using this, here we can have a comparison of the production of some of our main steel products. We have the average CO2 emissions per kilo of steel worldwide production, and X-carb, so the low carbon version of it. So we see that for some of the products we are able to reduce A1A3 production impacts global warming potential by up to 84%. So now if we have a look in the results, here we have the three variants that we assessed, the timber, the reinforced concrete, and we have two steel variants. The first one is to represent, let's say, steel average produced in Europe, and the second one is a sensitivity analysis using the low carbon emission steel from ArcelorMittal. And results are here also represented by life cycle stages. So the first thing that we see that the majority of the impacts are coming from the production of the products that we are putting in the building, and then we see that we can reduce up to 46% on global warming potential if we compare the low carbon version of steel with the reinforced concrete. And if we compare with the timber building, we see that average steel produced in Europe is more or less in the same level of emissions with the timber building, and we are able to reduce 26% of impacts if we use low carbon emission steel. But then if I show this graph here to a structural engineer, say that, okay, I guess that his feedback will be, okay, where should I optimize my building so I can really reduce the embodied carbon of it? And we like also to show results based on building parts. So here we see the same results, but instead of focusing on the life cycle stages, we are focusing on the building parts. Mainly we have the influence of the floors, the cores, foundations, frame, for example, and then we see that throughout all of our structural options, the most consumer of or emitter of CO2 are the floors. So the idea, so basically, in order to optimize office buildings, I would say, based on this assessment, we need to use less materials or greener materials, especially in the floors. Basically that. So then, to conclude, we saw that we can reduce global warming potential by using first a steel concrete composite structural option. And if we use low carbon emission steel, we are able to reduce 46% of global warming potential if we compare to the reinforced concrete, 26% if we compare to timber, and that's thankfully because of the high content of recycled steel and the use of renewable electricity in steel production of the low carbon steel. We also saw that the majority of the impacts are coming from the product stage, so that gives us a very good idea that we should use not virgin materials, but recycled materials. And also that we see that to be most effective, we need to optimize the floors because they are the building parts that are most emitting CO2 emissions. And with that, I finish my presentation. Thank you.
Thank you. Thank you very much for this presentation, José Humberto, on the influence of the structural design on the embodied carbon emissions. We will continue with a presentation from Nicolas Réhault from Fraunhofer Institut for Solar Energy Systems. And I'll put your slides.
Thank you very much. So welcome to my talk. José, I want to remove a confusion. I'm neither an architect nor a civil engineer. I'm either a mechanical engineer. But your talk was very interesting, and so you show how to reduce the carbon footprint of buildings. So it is here another way to do it. But at looking at the operation of the buildings, because you have here a lot of potential, because typically most of the buildings do not operate as they should do. And one way to do it is to develop and to apply fault detection and diagnostics methods. And the best way to do it is also to do it automatically, because the building produce more and more data, so huge amounts of data, and so you cannot analyze this data with human work. So you need to automate. You need machines to do this. And actually, there is no perfect method. And so basically, there are two types of methods. You have rule-based systems, so based on expertise. And on the other side, you have machine learning methods, so AI methods that you can train. And here we propose a combination of these two kinds of methods. And actually, what I present is not the result of my work, but the result of the work of Sebastian Dietz. He's a PhD student at the University of Luxembourg, but he's not here. He's in Austria. And so I will do my best to present his work. So here's the plan of my presentation. So a few background as objectives. Then what is the focus of our approach on analyzing the residuals, to do fault detection and diagnostics, and how we do a hybrid to methods to benefit of the strength of both approaches. Then we show a few case studies and a summary. So yes, indeed, the potential to save energy and CO2 in buildings is quite high during the operation phase. Typically, you can save, I would say, in means 10% in some cases, so up to 20%. We know from managers that they have saved much more, so much that they didn't tell it. So, because the buildings were operating so bad, and. To do this, at the moment it is quite a manual process, and it is very heuristic, so based on analysis on a lot of time. And what you can do, as I said before, is set up an automated process. But to set up this process, the implementation and parameterization efforts are quite high, which restrains the transferability from one building to the other one. And so this is what we wanted to address in our work. So basically, when you have a dynamic process, you have something, a pointer or something like that?
No, but I think if you... a presentator did point. Maybe this one?
Ah, the pen. Laser pointer. Ah, okay. Yes,
Yep.
thank you. So if you have a dynamic process like a mechanical system in a building, let's say a ventilation system, so it will take input, like for example the outdoor temperature to keep it simple, and produce an output with it, which is supply air temperature at a given temperature, so that it feels comfortable. Okay, sorry. So these processes, they can be impacted by different kind of faults. For example, it's a component who does not work as it should be, or there is fault in a sensor, for example, so in the process, and it will modify the output. And this is what you can observe if you put a model parallel to your real process. And your model, if well trained, if well set up, will also produce an output, and then you can compare the outputs of both real model and synthetic model, and then evaluate the residual. And this residual evaluation can help you then to detect fault and to diagnostic faults. And then you can integrate this result in a process, or for example, in what Igor showed us before, to enhance your smart readiness indicator. So now, when you have a real building, so you typically capture the data from the building, from building automation systems. So these BAS, which are the systems who control and control all the HVAC, so heating, ventilation, air conditioning systems. And you can collect historical data from these buildings to train your algorithm in the first time. So typically for buildings, you need at least one cooling period and one heating period. And here what we did is that we first, and this is a hybridation actually, we first cleaned up the data with a rule-based analysis. It's a set of very common rules, simple rules, to ensure that you can train quite properly your model without training it with fault, so to have a kind of nominal operation of your model. And then you can determine parameters for residual scoring by analyzing the residuals. During the application phase, so you can transfer this model to a real building. So new data are incoming. You can also here have a first analysis stage with typical rules, and with the developed machine learning models, you can then do with real data this residual calculation, evaluation, and then calculate a quality index and the results which can be exploited then. So the first step of this hybridation, so the rule-based part, so it was based actually from software that we have developed at our institute, so it is actually the basis of our collaboration. And this software, it's a set of expert rules that enable us actually to, as I said, to discover, so I would say, so low-hanging fruits, so typical faults that happen in the building. The advantages is that it's very simple. The implementation is quite straightforward. It enables also an immediate diagnosis, and it is highly specific if parameterized correctly. It means you have not false positive message. The drawback is that it is a bit difficult to transfer from one building to another one. It is very rich in parameters that you have to set. And it cannot detect faults that are not programmed. So the other kind of model, so here Sebastian used multiple linear perceptron networks. And so first he had to transform the data using a sliding time window. And what he did, he created one network model for each estimated variable. For example, as I said before, you have the supply air temperature, you have the exhaust air temperature, you have some room air temperature, so different kind of variables. And for each variable, you have one model. So the model was optimized using Bayesian optimization, so to find the best hyperparameters. And at the end of the day, it looks like this. It's just an example on how Sebastian generates residuals. So you have here the observed supply air temperature. You have here the prediction from the model, and you have here then the residual. And when this residual have a typical shape, then the algorithm generates a fault state. Yeah? So it springs from 0 to 1. And here we have the case that we have a central an air handling unit, excuse me, which is heating without using the heat recovery. And so regarding the determination of the score, because actually it is the core of his work. So here, if you see the density representation of the residual, so we have here in blue the fault-free data, and here we have the faulty data. And the scoring is done like this, that you have based on the percentile and how far the data are distributed beyond a certain percentile, then we will generate a score. So it means here we have a lot of data who are beyond the 5th percentile, so we will have a score of 1, so it is actually a very significant fault that has been detected. And it is done like this, as I said before, for all the variables. At the end of the day, we sum up all the scores. And we set up also a threshold empirically, so I think it is at 1.5 for all the variables. And if this threshold is then overrid, then it generates a fault signal. So the application, and also we made tests, of course, to assess the transferability of this approach, because it is one of the objectives. If you want to harvest all this potential in all these buildings, and you have to transfer very quickly from one building to another one. So we had here 9 different air handling units, different sizes and with different topologies. So one in Germany, in Berlin, with supply and exhaust air systems, plate heat exchanger and heating coil. We had also 3 here in Luxembourg. With here we had a heat recovery wheel and a heating coil and adiabatic cooling. And here it was another one, I don't know exactly the location, with the same actually topology as in Luxembourg. So actually there is not really a European specificity regarding the quality of operation of buildings. In all the countries that we have investigated, the buildings were not really good operated. So you have potentials everywhere. Here it's to show the effect of this hybrid method on the residual. So excuse me, it's in German here, but when we apply a filter with rules, we remove the danger that we learn an operation which could be faulty, and we say no, it's not faulty. And so you have a higher sensitivity of your machine learning algorithm. So it means you have the capacity to detect big quantity of faults. It is not ignored, it is not masked. And it is right with continuous variable, but also with a categorical variable or events, because you have, for example, supply air temperature, it's continuous, it varies, from so in a temperature band, but you have also events in buildings. So things goes on and so it's a binary signal if you want. And here you can improve the detection quality of the method by combining these two approaches. And another thing is that also the machine learning methods enables, of course, to detect novelties. So it means things that are not programmed in a rule, or things that a rule do not detect because a rule to be fired, if you want, or to be triggered, the rule needs to have the right input data. And with the machine learning approach, we are much more flexible. So we can cope with only a different set of variables. So this is what makes this hybridation actually interesting. And also with the hybridation, we have the possibility when both systems or both methods say it is a fault, you have a very high confidence in your detection. So regarding the transferability, so on these 9 air handling units, what we could calculate is that your sensitivity or fault detection rate is much higher when we have the scoring method, so based on these two methods, compared with a pure rule-based system. Of course, it depends on the quality of your rule-based system. Yeah, if you have a lot of rules, then you would be better. But as I said before, it is quite challenging sometimes to parameterize and to transfer. But basically, in all the cases, all the handling units that has been investigated, we had the best performance of this hybrid method. And I come actually to the conclusion. So a higher sensitivity. In case of bad training data or changing boundary condition, the risk of high FRR is for false alarm rates exist. Yeah, okay. Excuse me. So we can detect novel faults. So it means we have this high sensitivity when the rules cannot be implemented or when they are not there. And so at the end, we increase the whole performance. The next step actually is to transfer it to a platform, for example, to put it at a higher level, and to put it at the disposal of facility manager overview if you are interested for further exploitation. Thank you very much. If you have a very precise question, you write better an email to Sebastian. If you have question on exploitation, you can write me directly, because at the end of the day, it is my mission. And yes, wanted to thank also the European Commission, because actually we had, it was a direct contract between us and between the University of Luxembourg, but most of the things that we provided were developed in a European project. So this is what we were also allowed to present here, even if the project has been closed 2 years ago. Thank you.
Thank you. Thank you very much, Nicolas Réhault.
Thank you.
We will continue with the last presentation from Nirvana Marting from LIST on social LCA of recycled PVC products.
So good afternoon, my name is Nirvana Marting. I work for the LIST, Luxembourg Institute of Science and Technology, and today I will give a presentation on social lifecycle assessment of recycled PVC products. This is part of the Circle-STEAM project. I will explain the project in the following slides. So the content of this presentation, first I will give a short introduction of why PVC value chains, why do we analyze them. Then the Circle-STEAM project, objectives and scope. Then I will proceed with the methodology and introduce briefly what is a social lifecycle assessment, what are the impact categories that we are assessing, and then I will show some preliminary results because this project started this year and we don't have final results. And then finally I will give an outlook. So let's start. In 2020, the United Nations estimated that there were approximately 2 billion of tons of solid waste produced globally. We have an estimation from the OECD in 2022 that global plastic waste accounted for 353 million tons in 2019. And approximately 16 million tons of plastic waste were generated in the European Union. From the production side, it is estimated, Plastics Europe, it's another source, estimated that 5.3 million tons of PVC were produced in 2022. This is virgin PVC. And the European Commission estimated that 2.4 million tons of post-consumer PVC waste were generated in the European Union in 2022. I already said the year. And 44% were generated in the construction sector from this waste. We also know, there is an estimation from Vinyl Plus, that 70% of the PVC is used for products used in the building sector. So you see there the PVC applications in this. Where is the point? Yes, this is the pointer. You see in this scheme that PVC are used in pipes and fittings, window profiles mainly, flooring and other applications. I will jump this slide and let's go directly to the Circle-STEAM project. So the Circle-STEAM project tries to assess the sustainability of circular economy strategies, like for example plastic recycling, from the three perspectives: environmental, social and economic. But we know that circular economy practices are not sustainable per se, and for this reason we have to do this assessment. So this project is integral, covering the three dimensions. However, in this presentation I will focus on the social part. We have 3 working packages, and currently we're in working package 1. In working package 1, we aim to perform a conventional assessment. In working package 2, we will try to integrate the 3 pillars via cause-effect chains, and in working package 3, we will aim to combine these cause-effect chains and integrate the assessment into a conventional one. So the objective of this part that I'm presenting is to quantify the social issues and job creation of the PVC value chains. So let's explain what is a social lifecycle assessment. So in a social lifecycle assessment, we have 2 systems, similar as in environmental lifecycle assessment. We have a foreground system that you can see here. Those are the core processes that we're looking at. In this case, it could cover the whole value chain from PVC production, so the resin, manufacturing, use, waste collection, sorting, recycling, and the loop goes back and then incinerating. These are the foreground processes. What are the background processes are those processes that will supply inputs to our core processes. In the case of PVC production, we're talking about ethylene and chlorine production, for example. In manufacturing, we're talking about the energy needed for the manufacturing. And then we also cover the suppliers of the suppliers. This is also the case for environmental life cycle assessment. In a social life cycle assessment, we want to do this to analyze what are the impacts of these process units on involved stakeholders. So you can understand already that it is a very ambitious assessment from a social perspective. There are some frameworks. There is one specific framework for performing a social life cycle assessment. This is the guidelines. Here you can see the guidelines for social life cycle assessment of products and organizations. That is a document that was prepared by the UNEP, United Nations Environmental Program. And they present a framework in which they cover several stakeholders and propose different impact categories. We have, for example, workers with different impact categories like collective bargaining, working time, social benefits, health and safety. We have the local community, also with different impact categories like access to material resources and value chain actors. For this specific study, we will cover health and safety of workers and the employment for the local community. Why health and safety? Because there are two sectors intervening in the assessment, the construction sector and the plastic sector, and both relevant from this perspective of health. And yes, so the product system here I present not the complete processes I showed in the beginning, just to say that the linear system covers the PVC production and then the use and the value chain until the incineration without the recycling, while a circular system will cover the recycling. So what is the scope of the study? The geographical delimitation. We will cover Germany first in the beginning, and then Luxembourg. The stakeholders covered are workers and local community. The impact categories, as I said, job creation potential and health and safety. And the sectors I already mentioned, construction and manufacturing, the plastic sector. So what is the methodology for estimating the job creation? Well, we use input-output tables. In this case, I will talk about specifically about PSILCA, which is not an input-output table, but I will explain. And XIO-based version 3 monetary, which is an input-output table. And for the health and safety, we aim to use use docs to estimate exposure of workers to chemical substances. So what are input-output tables? So input-output analysis is an analytical framework that provides data of the structure of the economy based on the interdependence of industries. So basically, we know we have a country and sector one, country providing monetary flows to country and sector one, so inside a country. And then we have the different sectors, so country one, sector one providing to country one, sector two, for example. And then this data is collected at country level. And there are harmonization of these databases covering also different countries. And this is called multi-regional input-output table. So it covers various countries, various sectors, and you see the money flows that go from one sector to the other, depicting the whole economy, let's say. That is an input-output table. And for estimating the job creation, we use PSILCA and XIO-base. So PSILCA is a database for conducting social risk assessment, specifically. So a database that was developed within what is the field of social life cycle assessment. But it's based on a multi-regional input-output table that is called EORA. It covers 189 countries and contains worker hours by sector and country. XIO-Base is a multi-regional input-output table that covers 49 countries, mostly European, and five big economies, and regions, aggregated regions like rest of the world, Latin America, for example, or rest of the world, Asia. And they provide worker hours per euro, and also they provide total employment by sector. So, to explain a little bit how the PSILCA estimated the worker hours based on EORA, so basically we have as I said, the data in the input-output table, and then there is an account called compensation of employees by sector and country. So the amount of money that employees receive in a specific sector and country, and this divided by the total production of the sector and country. This is called the unit labor cost. And this unit labor cost is divided by the wages by sector country, and in this way you can obtain the worker hours. And as I said before, XIO-Base already contains worker hours accounts, so they are already provided. And now I will show the very first preliminary results. I have to work on this data, but I will show you. So we covered the different unit processes from PVC production. We included profile production because our case study is on window frames. Then we have the windows assembly, then the montage, so the people that goes and mount the window in a house, the unmounting, then the collection and sorting, the mechanical recycling, then again the profile production with a recycled PVC, the window assembly, the montage and mounting, sorting, and then incineration. I collected the data from from various sources. Some of this data is also from XIO-Base, for example, for the windows assembly and PVC production. Of course, that in XIO-Base you have sectoral data. So once you have the sector, you have to allocate some price or cost of the product to do the estimation. And what we can see here is that those processes that involve humans, basically like montage and unmounting, when we do the comparison in worker hours per PVC ton, are those that have the highest amount of worker hours. And this is because we are considering in PVC ton. Of course, in the processes of PVC production, they are highly automatized industries. And yeah, this is the reason. I have to improve the data with data from stakeholders at some point, or considering different technologies, for example, here in the sorting, yes, so preliminary results. So that is the first step. That is the direct jobs. So the worker hours, we have the worker hours, and then we can, using the full-time equivalents, we can estimate the number of jobs, full-time jobs. And those are direct jobs, but as I showed in a previous slide, when we're doing a social life cycle assessment, we care also about the jobs in the value chain. So the life cycle jobs, and therefore the life cycle hours. And there is an interesting publication, Mampilan. He explains the differences between direct jobs, what are direct induced jobs, which are jobs provided by a supplier and created to serve the project, so jobs provided by the supplier. The indirect induced jobs, jobs provided by the supplier of a supplier. And finally, we have the secondary jobs that we don't cover the secondary jobs here, but I can explain shortly what they are. Basically, when there is a project, and there is employment associated to this project, this employment will in turn generate other more employment. For example, if there is a project of construction, and then the people working for this need to eat or do some activities around the area, then they will induce the creation of other jobs for the people who had to prepare the meals and work in the other activities. But these secondary jobs, we will not cover them now. We will focus on the direct jobs that I showed the preliminary results, and the direct induced and indirect induced jobs, which we can calculate from the input-output tables. How? So here we have basically this way of calculating. Basically, we have the social matrix, that is the worker hours per monetary unit per sector and country. And we have the matrix of technical coefficients. And with this, we can estimate the worker hours in the life cycle. And that is exactly the data that is provided also by PSILCA. And now to show you how the results will look like in the end, I have to introduce this other project, which is the Calimero project. Calimero is funded by the European Union. It covers different case studies in the construction, woodworking, textiles, pulp and paper, and biochemicals. And they aim also to assess the environmental, social, and economic sustainability. Within this project, we analyzed some job creation for the pumice stone, which is a stone that is used in a process to wash jeans, textiles. And basically, what I want to show here is that I did a comparison between the databases. So the jobs estimated using PSILCA and those estimated using Exibase. And I found that there is a variation of 30 to 35% in the amount of jobs that both databases are throwing the results. And then we will also analyze the different skill levels. Because with Exibase this is possible, the data that they have in the input-output table has these classifications. High skill female, high skill male, so it's by gender and by skill, and we will also discuss this in the paper. And finally, we have some regionalization, because we are considering data from country sector. That means that the worker hours and the jobs created, we can know specifically where these jobs are created. Yes, so for example, in this case, a study of the pumice production, the jeans, the washing of the jeans with the pumice. This study was conducted in Turkey, so the case study takes place in Turkey, the core processes. And that's why we have Turkey as the main contributor of job creation, also because various of the inputs were also sourced in Turkey. But we can see that jobs are created also in other countries, India, China, Germany, France, and others. So finally, I will provide an outlook. Yes. As I said, I have to work on the data. I wanted to show you the way we are calculating this job creation. And also, we will include in the study health, human toxicity of different chemicals that workers are exposed to along the value chain, and physical hazards, for example, rate of accidents in the plastics and construction sectors. And references. Thank you.
Thank you. I think we even have time for questions, if anyone has one. Yes? Mm-hmm.
If you, in your analysis, because I'm afraid that to measure the social performance, the creation of jobs might contradict like a better cost and environmental performance. If you found those kind of results, because imagine that if you have a very automatized process that might lead to lower environmental or cost impact, as opposed to creation of jobs, perhaps. I don't know. You may find that, and yes, my question first is if you already found this contradiction between social and environmental and costing, and also if you, as opposed to, for instance, health and safety, I would say that an automatized process would lead, let's say, especially in construction, will lead to lower environmental, will accompany lower environmental impacts and lower costs. That will also lead also to health and safety of workers and so on. If you assessed the three impacts already together.
Mm-hmm.
I don't know if I was clear in my question.
Yes, thank you for your question. So in the project, we want to assess the three aspects and at some point integrate the aspects. Maybe also discuss, as you said, some trade-offs. But so far, no, I didn't really cover that part. So the environmental assessment was performed in other project, but we didn't get to that point. But I think we will do it, and also we will try to integrate the aspects with cause-effect chains. So, for example, the creation of how the creation of labor will impact, will have an effect in the environment. Yes, I have a slide from another presentation, but I don't have it now.
I guess what you meant is that, okay, maybe you have less, let's say, workers in the end of the chain, but by inducing automatization of the process, the beginning of the chain, you are going to generate a lot of jobs there, for example. So that's quite difficult to identify if that's going to happen or not. If we are just looking, for instance, at a construction site, so maybe you are reducing a lot of jobs in the construction site as opposed to, I don't know, in the beginning of the supply chain.
Yes, and now that you mentioned that, I think it would also be interesting to consider different technologies if possible, so to see how automation is influencing jobs. And yes.
Because you mentioned a case study of the PV structure of a window, if you plan to compare that with other solutions such as steel or aluminum, or not?
It is not planned within this project, but why? So.
Well, because it would be interesting to see how the different, how the PVC social assessment would compare in respect to the different materials.
Right, I understand.
But okay,
yes, thank you.